Okay, so we are studying Sturm-Liouville eigenvalue problems. This is the setup. We have an operator L. L acts on functions phi, and we've got p times phi prime, and then all of that, the derivative of all of that, plus q times phi. And over here, the domain of functions that this acts on, so we can put any differentiable function there, but we're just restricting its domain to functions that satisfy this given boundary condition. Where again, beta 1, beta 2, beta 3, and beta 4 are all given in the problem here. And we're looking at this eigenvalue problem, so L phi equals minus lambda sigma phi, and again, sigma, p, and q are all given, and they're real and continuous, and p is greater than 0, and sigma is greater than 0, and all of these properties hold on the interval a. So I'm not going to go over this every single video, but for the next several videos, I'm going to be giving a whole bunch of properties that the Sturm-Liouville functions, or solutions, eigenfunctions, and eigenvalues for this Sturm-Liouville eigenvalue problem satisfy. Okay, so the first one that I want to give is not really something about solutions or eigenfunctions, but it's something about it's a property of the operator itself, and it's going to be the following. So this is lemma 7.1 in the notes. And it says the following. It says, let phi and psi be two functions, and we want, second differentiable functions. So these are two different functions on the interval a to b. Then the following integral theorem holds. The integral from a to b of psi times L applied to phi minus phi times L applied to psi, and all of this is just integrated with respect to dx. This is equal to p times psi phi prime minus phi psi prime, and this evaluated from x equals a to x equals b. So you would evaluate this at b, evaluate it at a, and subtract them. They're both going to have to be there. Okay, so why is this true? Well, all we're doing to prove this is just going to be some integration by parts. And I'm basically only going to kind of prove the formula. Well, you'll see what I'm going to do here. So here's one. This is sort of the proof. All this is an application of integration by parts. So I'm going to look at the integral from a to b of psi times L phi. Well, what is L phi? I'm going to look up here. This is going to be p times phi prime, all of this prime, plus q times phi dx. And we see what's going to happen here is that, well, there's going to be some symmetry here. And this operator is, if we restrict this operator to just the domain of functions that satisfy this definition here, is a symmetric operator. If you've taken linear algebra before, you know what that means. Okay, so now what we're going to have here, I'm going to do this. I'm going to split this up, or I'm going to distribute the psi first. And this is going to be the integral from a to b psi times p phi prime prime dx, and I have run out of room here, so I'm just going to erase this and squeeze everything together. I'm just going to rewrite this but smaller. So we're looking at the integral from a to b psi times this, so it's going to be psi times p phi prime prime plus q times phi dx. I'm going to distribute the psi to both of these terms and split it into two integrals. For now, I'll combine it back into one integral in a moment. So this is the integral a to b psi times p phi prime prime dx plus the integral from a to b, and then we're just going to get psi times q times phi dx. Okay, so what I'm going to do on this integral, I'm going to do integration by parts to move the derivative from there to there. So I'm going to do integration by parts to move the derivative from there to there. And so when we do that, we're going to get p, so it's going to be, so like this term right here would be my v prime, because it has the derivative. So it's going to be p times phi prime times psi, evaluated from a to b, minus the integral from a to b. What are we going to get? Well, there's not going to be, the derivative is now going to be on the side, and this is going to be equal to psi prime times p times phi prime, because we've taken the derivative away from there, dx, and then plus this term, so now it's going to be plus the integral from a to b, psi q phi dx, like this. Okay, now what's going to happen, notice what's going to happen here. If I factor out a minus sign here, well, let me not do that yet. So I've got these boundary terms here. So p phi prime psi. That corresponds to this, p phi prime psi. Okay, so let me record this information up here. So this integral here, what I've said, this integral here is equal to what I have down here below. So this is equal to p phi prime psi from a to b, and then I'm going to do minus, and I'm going to combine these integrals back in, I'm going to combine this back into one integral. So I'm going to have the integral from a to b, psi prime p phi prime, but I have a plus there and a minus there, so it's going to be minus psi q phi dx. That's what I have. Okay, so I'm going to erase this. Now, notice what happens if I want to compute phi times L psi. Well, I can just interchange the roles of those. So now I'm going to have a to b times phi, and over here it's going to be p psi prime prime plus q times psi. But before I do that, notice that if you just look at the integral part right here, the phi and the psi appear in symmetric ways. So for this term, we have a p, but also a psi prime and a phi prime, because we did integration by parts. We moved the derivative from here onto psi. And then over here, it's psi times q, or psi times phi times q. So unlike here, if we look here, we kind of have a double derivative of phi and no derivative on psi. So this is not symmetric. Over here, it is symmetric. It's just a boundary term here that's not symmetric. Okay, so what I'm going to get then, if I just interchange the roles of phi and psi over there, well, here I'm still going to get a p. Instead of a phi prime, I'm going to have a psi prime. Instead of a psi, I'm going to have a phi, and this is evaluated from a to b. And then what am I going to get over here? It's going to be the exact same thing because of this symmetry between phi and psi. So this is going to be the integral from a to b, psi prime p, phi prime minus psi q phi dx. So in other words, these two integrals are equal to each other. Now in this computation, we're doing this integral minus that integral. That's what we have on the left-hand side. We do this integral minus that integral. Since these two terms are equal to each other, they just cancel each other out and they're zero, and all we're left with are these boundary terms, which is exactly what we have here. We've got this minus this, that's exactly what we have there. Okay, so this proves this computation here proves this. Now, the reason that we care about this is because if we know in addition that phi and psi satisfy the same homogeneous boundary conditions, then these boundary terms are equal to zero. So in other words, what we know is if phi and psi satisfy these same homogeneous boundary conditions here, then the right-hand side is equal to zero. Okay, so I want to prove that now. So I'm going to leave this lemma up here. I'm not going to erase it. I'm going to state the new lemma. And this is lemma 7.2. There's a weird typo where there's like a weird line on top of the omega. What has happened there? Okay, I've got a new Greek letter there. But I'm not really sure how it got there, but it's a typo for me to look at. Okay, so this is lemma 7.2. If phi and psi satisfy the same, I'm going to call it this homogeneous boundary conditions, meaning these boundary conditions over here. Homogeneous just means they have 0 over here. So if phi and psi satisfy the same homogeneous boundary conditions, and they're the phi and psi from this up here, then the right-hand side of the above is 0. The right-hand side of the above is 0. Okay, so what's the proof of this? All this is just a computation. It's just a computation. And actually what we're going to show is that this is equal to, well, let me show you what we're going to show. But we're going to show it's equal to 0 at A and at B. So what we're going to do then is we're going to replace, so I'm going to look up here, replace, let me write this is the proof. We're going to replace phi prime of B. So if we come over here, phi prime of B is equal to minus beta 3 over beta 4 times phi of B. This is equal to minus beta 3 over beta 4 phi of B. If we do that, and similar replacements for psi, what we're going to get then, if we just look at the B side of things, we're going to get psi of B times phi prime of B minus phi of B psi prime of B. This is equal, I'm going to come down here because I don't have enough room. This is equal to, okay, so phi prime of B is equal to that, so this is equal to minus beta 3 over beta 4 psi of B phi of B, and then minus, okay, so phi of B, but psi prime of B is equal to minus beta 3 over beta 4 phi of B, and then multiply this by psi of B. Well, these terms are equal to each other. Minus beta 3 over beta 4 psi of B phi of B. Over here, minus beta 3 over beta 4 phi of B psi of B. So this is equal to 0. So that's equal to 0. So if you evaluate this, again, if psi and phi satisfy the same non-homogeneous boundary conditions, that's important that the betas are all the same, so that the beta 3 over beta 4 is the same as that beta 3 over beta 4. So if phi and psi satisfy the same satisfy the same homogeneous boundary conditions, then this is equal to 0. And actually something a little more than that is true. If you plug in B to here, you get 0. And if you plug in A to there, you get 0. So if phi and psi satisfy the same homogeneous boundary conditions, what this means is that the right-hand side of that is equal to 0. And what that lets us say is the following. So what that lets us say is the following. So I'm just going to write this as a fact since I don't have it in the notes as a lemma or anything like that. If phi and psi satisfy the same homogeneous boundary conditions, then what do these two lemmas say? In conjunction with one another, what do they say? Well, if I look at the integral from a to b of psi times L phi, if I do this minus this, I get 0. So in other words, for phi and psi that satisfy the same homogeneous boundary conditions, the right-hand side is equal to 0. So in other words, the integral from a to b of psi L phi is equal to the integral from a to b of phi L psi dx, like that. So the integral of psi L phi is equal to the integral of phi L psi. So what we're saying then is we're saying that the operator L is symmetric if it's acting on this domain of functions. If we restrict the domain to just functions that satisfy these boundary conditions, what we're saying is that L is a symmetric operator. What does symmetric operator mean? It means that it satisfies this type of equation here. You might be more accustomed to seeing this like in linear algebra notation. We can write this as an inner product. So we would have something like L phi, the inner product of L phi and psi is equal to the inner product of phi and L psi. So these two guys are equal to each other. And again, that's what it means for an operator to be symmetric, is that on its domain, it satisfies this equality here. This is going to be very important in just a moment when we prove, in the next video, when we prove something about the orthogonality of eigenfunctions corresponding to different eigenvalues. But that's it for this video.